Hello, students. We are neck deep, actually, in the last section, 7.5 real numbers. This is where we tie together everything that we have kind of covered to this point with all the different groups of numbers. Remember, we started with the natural numbers. We expanded by bringing 0 in to get to the whole numbers. Then we brought in their opposites, and we got the integers. And then we said, well, what happens if we try to include division? So again, we were closed under addition and multiplication. Now we have an um, identity element for addition. Then we got a closure under addition, subtraction, and multiplication. And then we said, what about division? Maybe we can make that happen. And so we came up with the rational numbers. And the rational numbers are closed under division with the exception of 0. So it is don't divide by 0. Otherwise, they are closed under addition, subtraction, multiplication, and division, as long as you're not dividing by 0. And finally, we included, again, rational numbers were really cool. Anything that can be written as A over B. So that includes things like decimals that are terminating or repeating. Those can be written as a fraction. And so we're going to talk now about the idea of, well, wait a minute, what if there are numbers that are outside of this? Numbers that, if we wrote them in decimal form, could not terminate and they would not repeat. So we get this new group of numbers that we're going to see, and they branch off of the rationals, which means we cannot write as A over B. Okay, so if rationals can be written as A over B, things that cannot be written this way would be called irrational numbers. And the idea is that these exist. So what we're going to do is talk about them for a little bit, this section, and then we're going to kind of see when we put all of these together, all of them, we call anything in this group a real number. Okay, and that's the idea of this section. The section is kind of saying, hey, wait a minute, let's bring this all back together. So we've been expanding on operations. We started with addition, subtraction, multiplication, and division, but very limited on subtraction and division because for natural numbers, we had to talk about things like remainders. We couldn't talk about a fractional piece left over. Whole numbers, now we can talk about adding 0 and having a nice identity. With integers, we got not just the identity element, but the idea of an inverse. So we had our additive inverse. With rationals, we got a multiplicative inverse. So what that means is you can go one direction and you can go back. We've also talked a lot about exponents. And when we get to irrational numbers, we get to the idea of undoing exponents. And that is kind of like a root. So if you had an exponent of 2, undoing it would be the square root. And that's really what we're going to focus on here is kind of those connections. So hopefully this is an enjoyable path. So let's see here. The Greeks, it does go back a long time ago, the Greeks were the first to really study these numbers that are not rational. And they must be an infinite number of non-zero digits to the right. So it has to go on and on forever. And it cannot repeat. If it repeats at any point in time, you get a repetend, then we can rewrite it as a fraction, which would make it rational. So let's talk about some of these numbers. What do these numbers look like? What could some of them look like? And so you can come up with an irrational number pretty quickly. And you could do it with any collection. So let's say you want an irrational number of just 1s and 2s. Then you could say, okay, if I stopped at 0.1, that would be rational. So let me say not that. I'll say 1, 2. Again, if I stop at 1, 2, that's rational. If I put a bar over the top, that becomes rational. So what I need to do is I need to create some additional ideas here. And so I want you to take a look at this. There's definitely going to be a pattern here. So notice I write a 1, then a 2, then a 1, 1, then a 2. 1, 1, 1, 2. 1, 1, 1, 1, 2. So each time I am rewriting a string of 1s and 2s where I increase the number of 1s by 1 and keep the 2 the same. So there's one irrational number. I can't put a bar over it because it changes each time. So this would be an irrational number. Okay. What's another one? 0.12, 1122, 111, 222, 1111, 2222, dot, 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 dot. Again, pattern, but not terminating. As a matter of fact, you could look at these and see which one of these numbers, irrational numbers, is bigger by looking at their decimal expansions. You can see they match up perfectly through the first 5 digits. After that, the lower number has a 2, the upper number has a 1. So I could say if this was A and this was B, I would say, aha, A is smaller than B, even though they're irrational. Right? So that's the idea. And that's the definition of irrational. Now we have numbers that are similar to, that we symbolize, I guess, as irrational numbers, very specific ones. The one you probably know most is pi. And pi is approximately 3.14. It's not equal to 3.14. 22 over 7 is a good approximation of pi. Not great, but it's pretty good. And there are definitely ways that we can discover what pi is. We'll do more with pi in the geometry section. We'll kind of see where this symbol comes from, where the formulas that involve pi come from. So, a real number. What is a real number? A real number is any number that can be represented by a decimal. That means it's the union of the irrational and the rational numbers. Again, if it is a terminating decimal, that means it's a rational number. If it's a repeating decimal, that means it's a rational number. And if it's non-terminating and non-repeating, we would say it's irrational. So we're going to take a look now and say, let's talk about the idea of a square root. You've no doubt seen these. We've even done the square root of a number a couple times, just to make sure we're all okay with the definition. The square root of 25 would be, for example, a number that I square to get to 25. You can picture this over here as the sides of a square. And when I square a number, it means I create a square out of that number length. That's kind of the idea. So square rooting is going back from the value, which would be like the area, and trying to find the side of the square. So when we write this out, s squared equals 25. Just understand there are two solutions to this, right? S could equal 5. The side length could be 5, or the side length could be -5. Okay. So there are actually two square roots. When we write this symbol down, that symbol represents what's known as the principal square root. So if you write this symbol down, the principal square root is non-negative. That means usually positive, but if you took the square root of 0, we would say 0. So the square root of 25 with this symbol would be 5. Okay. Now, we would never say the square root of 16 is equal to -4 because the square roots would be non-negative. That's the principal square root. Okay. Phew. So there we are. The square root of a non-negative number a is a number such that we multiply it by itself and we get that value. Now, you'll notice they have restricted it. You cannot have, at this stage, a number that I square and get to -4. Now, later, you will see in math as you continue on, this is beyond the 8th grade level. So we're stopping at the 8th grade level, again, K through 8 for this course. You take this and you could say, well, n is equal to then plus or minus square root of -4. Now, as you go through this process, you end up with what's the square root of a negative number? And it turns out it is not one of these numbers that we've seen before. So it's outside of the real numbers. And so what we do in math is when we see something and it actually becomes a concept that's usable, we create something that is usable in that solution. And so we say the square root of -1 is defined to be I, which we consider a number. It's just outside of that group that we already talked about. So we would call this a non-real number. And if you've taken other classes, you might have heard this called the imaginary number. And it's kind of a cool number because if you square this number, you get back to -1, which again is not possible with the real numbers. Any real number that you square cannot be negative. Okay, and that's actually listed right here. Very cool. Let's jump into the next page. So find the following: the square roots of 144, the principal square root of 144, the principal square root of 4/9, and the solutions of x squared equals 5. So if you take a look, there are some samples here. We can go bigger than square roots. This is pretty common. So again, if you had like a problem, x cubed equals, let's see here, 27, we could think of x as being the cube root of 27. And just like there were 2 square roots, it turns out there are 3 cube roots of this. 2 of them might include imaginary numbers, and one of them that you might be able to calculate is not like that. One of those actually turns out to be a really nice number 3. So what we're doing is when we write these out, we will actually have the symbols that look like this. And this piece, the little n, is called the index. And whatever's there, we would say is the nth root. So if it's a 3, we say it's the 3rd root. Okay. And yeah, I think that's the biggest piece. Index. And so what is this? This value right here, whatever this thing is, and I'll put a little cloud down here, is that this cloud raised to the nth power is equal to b. So that's how we kind of connect these two together. And you can see it written here. The nth root of b raised to the nth power is b. And again, that's when b is non-negative. All right, so let's see here. 4th root of -16 does not exist as a real number. That's how we would say it. We don't want to say it does not exist, period, because it does exist, just not in the world of real numbers that we were dealing with. Again, real numbers are just those that can be represented as decimals. And so that's the big piece here. So, couple pieces to remember. The square root of a number that is squared is the absolute value of that number. Square root of x squared would be the absolute value of x. Why is this important? Remember, the square root being an absolute value would mean that this is never negative. Okay. But if you started with a negative number, your result may look that way because I'd have to say it's the opposite of x. And here's an example. If I say, what's the square root of -2 quantity? -2 squared, we would say, is +4. The principal square root of +4 turns out to be 2. But if I started with -2, what did I end up with? In this situation, I ended up with +2, which is the opposite. However, if I had started with the square root of +2 squared, that would also be this principal square root of 4. And the principal square root of 4 is 2. So in this case, they actually do match. So we needed something mathematically that will match when it's positive and be the opposite when it's negative. And that's why you'll see the absolute value here, because the absolute value does exactly that. Okay. Cool. Let's move on. School book page with some of these. Again, this one does go up to grade 8. And now we're going to talk about what kind of numbers are not rational and why they are not rational. So I'm going to jump into another slide here. All right, so let's take a look. We're going to start with the number, this is a pretty common one, the square root of 2. Now there's a couple ways to prove this. So let's prove it. Remember, proving it means I'm showing you that it has to be true. So I'd like to show that the square root of 2 is irrational. Okay, that's what I want to show. So here's what I'm going to do. Now, this is going to seem a little bit strange, but I'm going to make an assumption. I'm going to claim that it actually is rational. And then I hope along the way, I end up with a major fail, like two things that can't happen. And if that occurs, then it's because I assumed that they were rational. And if you do that, you assume that it is rational and you try it and it fails, you can go back to your statement and say, then it cannot be rational. So let's start with that. We're going to assume square root of 2 is rational. And what does that mean? Remember rational? Ratio. So that means the square root of 2 is equal to a over b as a ratio, right? And I'm going to add one more piece. I'm just going to go ahead and say, hey, let's just simplify this. The GCD of a and b, if you could, simplify that fraction down, whatever it is, so that the GCD is 1. Okay, that means a and b are relatively prime, no factors in common, so I'm ready to go. Now we can, because I made the assumption that it's rational, I now have this statement which is true based on my assumption. So let's see here. Square root of 2 is equal to a over b. Let's do things because they're equal. We can multiply both sides. So square root of 2 times b equals a. So we can do that. Again, these are because they're equal. Multiply both sides by b. Or you could think of this as the definition of division, like a divided by b is equal to this number if and only if square root of 2 times b equals a. You could use either one of those. Now let's square both sides. Because again, if they're equal, then if I square them, they will remain equal. So let's see here, square root of 2 times square root of 2 is just 2. b times b is b squared. And a squared is what I get on the other side. So I've got this really interesting equation now. Let's see here. What do I know? Well, let's take a look at this. I have a left-hand side and I have a right-hand side, and they are equal. Well, let's go back to chapter 4. I know that the left-hand side has a multiple of 2 in it. Like it has to. So I know 2 divides 2 times b squared. It has to, right? Because it's a multiple of 2. So 2 has to divide that. But that means is that 2 has to divide a squared. Why? Because they're equal. So 2 has to divide a squared. And this is the fun one. This is where the fundamental theorem of arithmetic comes in. If 2 divides a squared, then 2 has to be a prime number in a squared. So 2 must divide a. And this is by the fundamental theorem of arithmetic. Perfect. Phew. 2 divides a. Well, that is great. So now we know if something divides a, that a must be equal to 2 times I don't know what, some number. And if a is equal to that, then a squared is equal to 4 times k squared. And now I'm going to bring back in what a squared was equal to, because that means that 2b squared equals 4 times k squared. And now I'm going to divide by 2 on both sides. And that will leave me with b squared equals 2 times k squared. Oh, let's see here. So 2, so now 2 divides the right-hand side. And 2 must divide the left-hand side, which is b squared. So 2 divides 2 times k squared means 2 has to divide b squared because they're equal, which means 2 has to divide b. And it may not seem like much, but take a look right here. 2 has to divide A, and 2 has to divide B, which means that the GCD of A and B has to be greater than or equal to 2. They have to have something in common. But look what we started with. I'll bring that down over here. But GCD of A and B had to equal 1. We said that right up here. We said we're going to reduce the fraction. We reduced the fraction. So the GCD is equal to 1. But the GCD has to be greater than or equal to 2. This is a contradiction. Both cannot happen. All right, so both cannot happen. That means we have something that has failed miserably. And because it failed miserably, we have to go back to our assumption. I'll put a sad face here. Okay, both cannot happen. So we go back to our assumption, which was the square root of 2 was rational. And all of this trouble started because we said this is rational. And if it is rational, then we end up with a contradiction. Our final state would be therefore what? Square root of 2 must be irrational. So if you want to show why it's not rational, you start by saying, hey, let's just pretend that it is rational. All right, let's see what happens. And we end up saying that both A and B have a factor of 2, if this is true. Now, this entire proof could be redone for the square root of 3, or the square root of 5, or the square root of 7. And all of these are also irrational numbers. Any square root that's not a square root of a perfect square is an irrational number. So there we are. Let's see. Let me do one other way of proving it. I'll start with another one, which again is to assume the square root of 2 equals A over B. Okay, and we'll move along to where we were, which is 2b squared equals a squared. We get here. And now here's another approach to this that you could use. This one's kind of nice. This one's maybe a little bit shorter, but the first one I think kind of ties in some more of the ideas, but they both work. So let's take a look over here. The number that is the exponent, let me just write that. Exponent on 2 on the right-hand side is even. And you can look over here. Now, if there's a 2 in A, it would be 2 to some power. And then remember, we're squaring everything, so we square it. So the exponent must be even because we'd multiply those together. So the exponent on 2 is even. On the left-hand side, again, this is the exponent on A squared. The exponent on 2 in B squared is also even. Again, anytime you take a number and you square it, the exponents have to be even. Okay, could be 0, could be an exponent of 0, but that's still even. So 2 times B squared has odd exponent on the number 2. Because remember, I have an even exponent from B squared, and then I basically, when I multiply by 2, that increases it by 1. So the left-hand side has odd exponent on 2. Right-hand side has even exponent on 2. But what's the problem with that? These are equal. They're equal. And if they're equal, then the fundamental Theorem of arithmetic says your exponents must be the same. Fundamental theorem of arithmetic says exponents must be the same. There we go. Exponents must be the same. If the exponents must be the same, we have a contradiction. We have a contradiction. So square root of 2 cannot equal a over b, and the square root of 2 is irrational. There's another way to go. So the first one included violating the GCD, the greatest common divisor of both. The second one violates the fundamental theorem of arithmetic because I have an odd exponent, an odd number of 2's, and an even number of 2's. So a lot of different ways you can go about these proofs. You have to pick one of them. And the book uses the prime factors. We have an even number on one side, we have an odd number on the other side, and that's a contradiction that was caused by the assumption. Therefore, it cannot be a rational number. Let's see here. We do use irrational numbers geometrically, so it's not like they don't exist. They exist, and you can actually demonstrate their length precisely using something like the Pythagorean theorem. We'll do a lot more with that next term when we do geometry. We'll even see how to prove the Pythagorean theorem is actually true. For now, we can just use something like a triangle that is isosceles with a 1 and a 1. And if we use the Pythagorean theorem, this missing side, this hypotenuse, is an irrational number. And again, this is mind-blowing if you used to think, hey, everything can be represented in the form of a rational number. And now you could say, actually, it can't. This one cannot. So there we go. There's actually a fun way if you're actually doing these, and we will build this next term, but if you start with the little compass and you just turn, a compass is the thing that looks kind of like this, and it has kind of a pointy part here and usually like a pencil stuck onto it there. So when you put the pokey part into the hole and then you turn, it'll kind of turn and make kind of an arc of a circle. And so if you do that and you go 1 unit out and then you put the pokey part here and turn up, when you create this 90-degree angle and you get sides of 1 and 1, and you get this beautiful square root of 2, you could actually build another one coming out here with another side of 1. And what's great is you end up with the square root of 3. And then you build another one with the 1, and you come over here and you get the square root of 4. And you get this beautiful, what looks kind of like a spiral, because it keeps getting larger as it goes. It's known as the spiral of roots. Very beautiful. It's beautiful. And so I'm sure some of you are going to take that and incorporate into drawings for your home. All right. Let's see here. No, there it is. Estimating a square root. Square roots are very interesting because there is a process. If you want to know, there used to be something taught in even elementary schools on how to manually calculate the square of a number, the square root of a number. It kind of fell out of favor when calculators came in, so we were able to kind of use more with calculators. But you should still be able to kind of tell something. For example, the square root of 37. What we know is the square root of 37 must be bigger than the square root of 36. We can see that again, 37 is bigger than 36. And likewise, it must be less than the square root of 49. So even if you don't know what this number is, you could still come down and say, I know the principal square root of 49 is 7. Principal square root of 36 is 6. And you'd be able to say that the square root of 37 is somewhere between 6 and 7. Now, if you want numbers that are a little bit closer, you can keep going down more in terms of decimals, right? So what would that mean and what would that look like? Let me grab Desmos to kind of illustrate this because I think it's helpful to see. And you can grab your calculator if you want. Let's jump over to Desmos. Okay, Desmos. So here we go. Floop, floop, floop. Okay, so here's what I'm going to do. I want to take 6.1 and I want to square it. Now take a look. 6.1 squared is 37.21. So that's too big. So I could write this down. Let me get a little bit of white space over here so you can kind of see, hey, wait a minute, what would that look like? What I just found out from my calculator is I know that the square root of 37 is actually less than 6.1. Why? Because 6.1 squared is bigger. Okay. And we know that this is actually already greater than 6.0, which would just be 6. So now I've actually approximated this value to one decimal place. I could keep going and I would say, okay, now let's try some other numbers. Now this is where I do a little trial and error. 6.1 is too big. Why don't I try 6.05? 6.05 is 36.6. Okay. And I could try 6.06, 6.07, 6.08, and 6.09. And I hope you noticed there 6.08 is a little bit below 37, and 6.09 is a little bit above 37. So just using my calculator with multiplication key, I could find out that we're actually at 6.08 for the square root of 37 and 6.09. Again, somewhere between those. You want to get more accurate than that? Okay, let's go back and we add some additional digits. So I'd say 8, 2, or sorry, 8, 2. I said 2 and I wrote 3. So 6.082, if I square it, that's a little bit below 37. 6.083, that's a little bit above 37. So if I'm writing this out, now I know I'm getting closer and closer to that value. See what I'm saying? We're getting closer and closer. Now I could say, if I wanted to put a decimal down, I could say square root of 37 is approximately 6.08. I could get there because I've got it now measured out to 3 decimal places. Okay, but we could keep going and going and going. Now, it's not that exact algorithm, but when you come in and you actually want to take the square root of 37, a different mathematical process gets you to this number behind the scenes. That's what the calculator is doing. It's actually doing a math formula. We just don't tend to teach that formula. It's a little bit beyond what we cover. So 6.082, you notice I got to 6.082 just with multiplication. So this square root button was absolutely fundamentally changed mathematics for quite a while. There were teachers who said, no, you can't use a basic calculator if it has a square root function because they wanted you to do the square roots by hand to calculate them. So thankfully we're past that and we're moving on to where many things are understood and we can understand kind of what it means. And please understand, if you write this out to 5 decimal places or 6 decimal places or all the decimal places, that is not equal to the square root of 37. Okay. If you'd like me to show you why, just write it down and start doing the multiplication. Okay, multiply these. If this is equal to 37, the result should be 37.000000. I should get zeros the whole way across. But the first one I do is 3 times 3, and that gives me a 9. So fail. It is not going to equal the square root of 37. It's going to be very close to the square root of 37. And if I continued doing this, I'd get 3, 0, 9, 15, 6, 7, and I could keep going. And when I bring the next one in, I do all zeros because I'm multiplying by 0. Next one is 2 digits in, and I get a 9 here, a 0, 9, 5, 7. So again, as I multiply by these digits, it just turns out that I might have 37.00000, and then at the very end, there's just a 9 floating. So it's not equal to the square root of 37. It's just very close to the square root of 37. Okay. Cool. So that is something. Understanding that we can approximate them. And honestly, when you start thinking about what would I do, Scott, with my elementary school students or my students up between kindergarten and 8th grade, you would be utilizing this skill to help them approximate numbers. So like if you saw the square root of 70, right? Right off the bat, you're like, a lot of you are like, I don't know how big that is. But go back to what you do know. You know things like 8 times 8 is 64. 9 times 9 is 81. So you would know that this number has to be bigger than 8, and you would know that this has to be less than 9. So if nothing else, you have an idea of about how big this number is. And that piece right there is called number sense. And it is something that not just Common Core, but math teachers for decades have been trying to push upon their students, like, you can do this, to try to understand them. We drew this picture in class. This is the real numbers. Real numbers are comprised of the irrationals and the rationals. Don't forget the rationals are linked. Rationals include integers, they include whole numbers, they include natural numbers. Irrational numbers, they include S. They're called S, which I think comes from a long time ago, that when you were doing constructions and you constructed something that was not this rational number, they would call it a surd. S-U-R-D. Yeah, I know. Don't remember how I know that either. I just remember some class, they're like, well, construct the surd. And I was like, what the heck is a surd? So S is probably for surd. Q, you would think Q should be R for rational. We reserve R for the real numbers, which means when we get to rational numbers, we need something that forms a different symbol. And here, A over B, we think of that as a quotient, like division. And so that's where the Q comes from, is quotients or divisions. That's where that comes from. Let's see here, integers, we already know about positives and negatives. And again, sometimes you'll see this written with a Z. And the reason for that is sometimes Z is used for integers and I is used for irrationals. It just depends on the book and the curriculum that you are using. All right, what are all the properties of real numbers? Well, identity, inverse, real numbers have all of these properties, which is fantastic. And remember, the inverse property for multiplication is true for any non-zero number A. So this is something we've talked about already. We know we can't find a multiplicative inverse for 0. So you're closed on addition, subtraction, multiplication, and division, with one exception of division by 0. So we exclude that because you're still closed on every other division. We have distributive property, multiplicative, we have denseness property. All of these hold true. In this chapter, you'll also be asked to order the real numbers, which means you might have irrational numbers mixed with rational numbers, and your goal is you should still be able to turn them to decimals and see which one is bigger. They'll ask you, hey, find a repeating decimal between square root of 2 and 1 4/9. This is kind of fun, actually. When you're looking at it, 1 4/9 just has 1.444 forever. We've already seen that. Square root of 2 is 1.414. So if you look and say, what's between them? 1.4444 all the way, 1.414, 2, 1, 3, dot, 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 dot. Okay, so now you know that your number that you pick has to start with a 1. The next digit has to be a 4. After that, you have a lot of options here. Okay, if you want a repeating decimal that's between them, you have so many choices. Like, I'm not even kidding. So you could do 4, and the next digit could be as they did, they said a 4 and a 2. Perfect. Go ahead, do a 4 and a 2, because the 2 will put you between them, and then if you repeat it, it doesn't matter. You're already between them. So that's fine. 1.42. 1.43 would also work. 1.42 with just the 2 repeating would work. 1.42 and a 7 where the 7 repeats. 1.435 with the 3-5 that repeats. Wait, with the 4-3-5 that repeats. Again, infinitely many options here when they say find a repeating decimal. So don't think that you have to go too in depth. Find one, you're good to go. Okay, that is it for that. Let's go to the last piece, which I believe is radicals and rational exponents. Now, this is one where, again, some of you may have seen this in your prior math classes, but you may not have. And here comes the fun. Square root of 4, we know the square root of 4 is 2, the principal square root. So think about that. If I said the square root of 4 multiplied by the square root of 4, well, that would be 2 times 2, which is actually just 4. And if we look at this like, treat this square root like exponent, then that would be the same as the square root of 4 times 4, which we know is the square root of 16, which is also 4. So that's kind of convenient right there. Okay, so now if I want to think about that, and I want to get back to 4 itself, the square root of 4 times the square root of 4 is 4 itself, which is 4 with an exponent of 1. You now have something over here that you are squaring. So the square root of 4, if you square it, we end up getting back to 4 to the first power. So if we were to think, what exponent would I write so that, like, what exponent would I put up here so that I can square that and get back to 1? This exponent, this is what mathematicians do. We solve problems. This exponent would have to be a 1/2. Because a 1/2, when you raise it to the second power, you're going to multiply, which means you're going to end up with 1. So the square root of 4 is the same as 4 raised to the 1/2 power. Let's jump over to Desmos just to make sure you can kind of see this in action. Okay, there's the square root of 37. Now watch this. I'm going to do 37 raised to the 1/2 power. And what you'll notice is you get exactly the same decimal approximation. And that's kind of a quick way to go about doing some of these. So square roots are the same as a 1/2 power. Now, you can continue this. If you wanted a cube root would be the same as a 1/3 power. So all of these pieces have corresponding undo options. So when you look at them, you'll see things that look a little bit, maybe pushing you a little bit, but if you say x to the 1 over n power, well, that's just the nth root of x. And if you had x to the m over n power, think of that 1 over n first, and just say that's the nth root of x to the m power. Okay. Same rules apply with exponents that have applied before. A negative exponent is the reciprocal. Raising a product to a power is the same as the power, the product of the powers. And so that means when you are taking roots of numbers, you get roots that work with multiplication. So just like they did before. So that's what's really kind of cool about these is if you did the square root of 30, that would be the same as the square root of 6 times the square root of 5. But you got to be really careful. The square root of 25 is not the same as the square root of 16. Actually, it is 16 plus 9, but it is not the same as the square root of 16 plus the square root of 9. That's going one step too far. If you remember your order of operations, and maybe I'll group them this way from here on so that you can remember these grouped together. Exponents distribute over multiplication and division. Multiplication and division distributes over addition and subtraction. Okay, but exponents, if they try to go over addition and subtraction, it's just not true. Square root of 25 is 5, but the square root of 16 is 4, the square root of 9 is 3, and I got to tell you, 5 is not the same as 7, so it does not work. So they'll give you a few to practice here with your exponents. And you can do these on your calculator as well. They're asking you to try a few of them without a calculator, so you can kind of do some factoring. When you see 125, you know it ends in a 5, so factor out a 5. When you see 16, you know it's even, so you can factor out a 2. Or the last two digits are divisible by 4, so you can factor out a 4. But get down to prime factors with these, and it's usually a little bit easier to do them. That's my tip for those. And that wraps it up. Very cool. So that is it for us in Math 105. All right. Hope that works. If you have questions, let me know. Otherwise, off you go.